Hi everyone! Welcome to the last video from the series on the maximum likelihood method. The topic today will be template fits, and the video will be quite technical. It is very important to discuss template fits in detail because they are extremely common in particle physics nowadays. The point is that we hardly ever know our model in such a way that we would be able to build a PDF and fit it to the data. Our model consists of complicated theory predictions together with the response of very complicated detectors to particles. People sometimes manage to build a PDF describing all this, but a very common approach is to build the so-called templates with the use of simulated Monte Carlo events and fit their combination to the data. A big advantage of template fits is an easy handling of systematic uncertainties. Templates are histograms, in fact, and obviously we are going to do binned maximum likelihood fits. Systematic uncertainties are introduced as free parameters, and each of these parameters is constrained by some prior knowledge. In summary, we are going to talk about constrained, binned maximum likelihood fits today. Let's go! Let's denote the data histogram and vector. Then we have histograms of simulated data. Typically we have several Monte Carlo samples and therefore several histograms based on the Monte Carlo. Each of them corresponds to one physics process. For example, there's a signal Monte Carlo sample consisting of events we focus on. The signal can be the Higgs boson, quartic gauge coupling, production of four-top quarks, some new exotic theory prediction, and so on. Then there is one or several samples describing the background, events due to known processes that result in the same signature in the detector as the signal. A typical background processes are TT-bar production, W or Z production, combinatorial background, cosmic muons, and others. Let's denote the Monte Carlo histograms nu pi. Here, P stands for some specific process. Monte Carlo histograms are normalized to the cross-section of a given process. The weight assigned to each Monte Carlo event can be written in the following way. Wi is equal to Wimc times L int sigma p over sum of Wimc. In this formula, Wimc is an internal Monte Carlo event weight whose origin is deep inside the Monte Carlo generator. L int is the integrated luminosity and sigma p is the cross-section of the process P. For some generators, like good old Pythia, these weights will be equal to 1, but if you use modern NLO generators, they will produce weights different from 1, and a fraction of weights may even be negative. Together with these Monte Carlo weights, you can also use any other correction factors that are needed to improve your Monte Carlo simulation. The final event weight is then just product of the Monte Carlo weight and all the correction factors. As a side remark, let me say that templates for some background processes can be estimated from the data. However, they are treated in exactly the same way as the Monte Carlo histograms in the template fit. When all templates are built, we can sum them up to get an expected number of events in each bin. We can write nu I is equal to sum over p, mu p, nu pi. Obviously, nu pi stands for the expected number of events in a bin I coming from a process P. Terms mu p are typically free parameters that are to be estimated in the fit. The event weight Wi is constructed in such a way that the estimator of the normalization factor μp should be close to 1. Actually, not all processes need to be assigned a normalization factor. If the factor is omitted, then the expected event yields are fixed to the Monte Carlo prediction for the process in question. Typically, the normalization factor for the signal process is free, and it is called the signal strength. Finally, the likelihood function is a product of Poisson distributions. L of mu vector is equal to the product over I going from 1 to n bins of Poisson distributions of ni with the parameter equal to sum over p mu pi. Unfortunately, our Monte Carlo prediction can suffer from a limited number of events. This is quite common because the simulation of the detector response to final state particles can be CPU time consuming. Therefore, we have to take into account statistical uncertainties of bin contents of our histograms. We've shown how to estimate the uncertainties in the previous video. To take the Monte Carlo statistical uncertainty into account, we insert a set of new parameters and Poisson terms into our likelihood function. Each pair, parameter plus Poisson term, corresponds to one bin of one histogram. The likelihood function looks like this. L of parameters mu p and gamma pi is equal to the product over I equal to 1 to n bins, Poisson distribution of ni given the parameter sum over p mu pi gamma pi times product over p Poisson distribution mpi with parameter mpi times gamma pi. In the formula, MPI stands for the effective number of events in a bin I of a histogram corresponding to a process P. Effectively, each Poisson term represents an auxiliary measurement of the effective number of events whose goal is to determine the parameter gamma pi. In practice, people assume that the free normalization parameters mu p are close to 1. Then it is possible to reduce the huge number of parameters gamma pi to 1 for each bin. The likelihood function becomes L of parameters mu p gamma I is equal to the product over I equal to 1 to n bins Poisson of ni given the parameter sum over p mu pi, all this times gamma I, times a Poisson distribution of mi with expected value mi times gamma I. Here, the number mi stands for the effective number of events in a bin I of the stack of all histograms. A big chapter where the template fit turns out to be extremely suitable is incorporation of systematic uncertainties into our model. In particle physics, systematic uncertainties arise mainly from the following effects. One huge set are typically theory uncertainties. They are due to fixed-order perturbative calculations, modeling of non-perturbative effects, limited knowledge of parton distribution functions, if they are involved, and so on. Another important set of systematic uncertainties is due to the imperfection of the detector simulation. Between the real and the simulated detector, there can be differences, for example, in object reconstruction and selection efficiencies, object energy calibration and resolution, and others. Each difference has to be quantified and corrected for. However, the quantification comes with an uncertainty. Obviously, there are yet other sources of systematic uncertainties, like uncertainties on data-driven background estimates, luminosity uncertainty, uncertainty on the amount of pileup, and so on. Numbers like 100 sources of systematic uncertainty aren't rare in particle physics at all. In order to estimate the effect of each systematic uncertainty source on the predicted event yields, we shift the relevant underlying parameter by one standard deviation and we repeat the full Monte Carlo analysis. This way, we create a new set of Monte Carlo histograms. Let's denote their bin contents as nu pi plus delta pi, where delta pi is the difference in the event yield predicted by the varied and the nominal histogram. Moreover, people typically take into account asymmetry of the systematic uncertainties by evaluating up and down variations of the underlying parameter separately. This gives us two variations in the predicted event yield. We will denote them as delta pi plus and delta pi minus. Therefore, we have estimates of the event yield for three situations: shifts by plus and minus one standard deviation of the underlying parameter, and no shift at all. In order to get estimates for situations like shift by plus 1.27 standard deviations, we parameterize the predicted event yields like this: nu pi of alpha is equal to nu pi plus delta pi plus times alpha if alpha is greater or equal than 0. Nu pi plus delta pi minus times alpha if alpha is lower than 0. In principle, this linear parameterization is not mandatory, and one can write in general nu pi of alpha is equal to nu pi plus delta pi of alpha. Nevertheless, it is very convenient to choose such parameterization that delta pi of alpha is 0 when alpha is 0. Therefore, alpha equal to 0 corresponds to our best knowledge of the underlying parameter. Finally, we add up all variations due to the different sources of the systematic uncertainty. Nu pi of alpha is equal to nu pi plus sum over k delta pi k of alpha k. Next, we have to choose appropriate constraint terms for the parameters alpha k. Indeed, we are building a constraint likelihood function, and we are doing it in the way we described in the previous video. Actually, determination of the difference between the real and the simulated detector, together with estimation of the associated uncertainty, is, in fact, a supporting measurement. Justification of this treatment for the theory uncertainties is much weaker. Nevertheless, people work with theory parameters in this way very often. The most common choice for a constraint term is the Gaussian distribution. However, other choices are possible as well. Inserting everything into the likelihood function yields L of mu vector, gamma vector, alpha vector is equal to the product over I going from 1 to n bins, Poisson of ni with the expected value of sum over p mu p, all this times mu pi plus sum over k delta p I k of alpha k, and all this times gamma I. The next term is Poisson of mi with expected value mi gamma I. And finally, product over k, normal distribution of alpha k with mu equal to 0 and sigma equal to 1. Recall that we have one normalization parameter mu p for each free-floating Monte Carlo histogram. We have one gamma I parameter for each bin of our histogram. And we have one parameter alpha k for each source of systematic uncertainty in our analysis. Usually, we don't care about most of the alpha, gamma, and mu parameters. In the particle physics jargon, we call all parameters we don't care about nuisance parameters. Of course, we should have at least one parameter of interest. Otherwise, we wouldn't bother with all this complicated construction of the model. And that's it. Now that we have a likelihood function, we can extract the parameter estimators and their uncertainties. In order to extract uncertainties of the parameters of interest, we usually use likelihood profiling, which is nothing else but our good old graphical method. Recall that the graphical method implementation in MinV2 is called MINOS. If you just started to ponder how would you implement such a complicated likelihood in root or rootfit, then don't worry. Of course, there are tools already available that will do it for you. The most common of them is called HistFactory, and it is already part of the root framework. There is also a new, much faster implementation in Python called PyHF. It is unfortunately still under development, but it can already do most of the stuff that the old HistFactory can. With this remark, we close the chapter on the maximum likelihood method. But don't be sad. You will see that the likelihoods will continue cropping up throughout the rest of this course, and possibly also throughout the rest of your life.